So we're going to do an experiment to figure out how strong the gravity is on the surface of the Earth. And we're going to compare it to the force of gravity of the sun on the Earth. And we can combine those two things together to figure out how much more massive the sun is than the Earth. And to do this, we need a few things. We need a swing, and we need a volunteer to swing in the swing. And we're going to use a stopwatch to measure how long it takes to swing 10 times. And the last thing we need to know is how tall the swing is. So we have a measuring tape to do that. So what we're going to do now is we're going to swing 10 times. So here it goes. Are you ready?
Yep.
Okay. Ready? Oh. Go. So 1, 2, and 10. So that works out to 38 seconds. So the second part to make it work, which is a little bit more difficult, is measuring how tall the swing is. So what we're going to do is you'll stop swinging, and I'm going to just push the tape up the rope, and it's a little bit tricky to keep it going. Woo! It's almost there. It's 11 feet from the top to the bottom.
It sure is.
Using what we measured outside with the swing, we can figure out how much the acceleration of the Earth is to the swing, and we'll compare that to how much acceleration the sun exerts on the Earth. And we can use those together to figure out the mass of the sun compared to the mass of the Earth. So what we're going to start with is using Newton's law of gravity, where we have the mass of the sun divided by the distance to the sun squared times Newton's constant. That gives the acceleration of the sun on the Earth. The second element is what is the acceleration of the swing by the Earth. And that looks very similar. That's Newton's constant of gravity, big G, times the mass of the Earth, divided now by the radius of the Earth squared. On the other side of the equation, we're going to use what we measured and also what we know. So the first thing is, what is the rate of acceleration of the Earth going around the sun? And that's given by the rate that the Earth goes around the sun, which we call omega, and we have to multiply it by itself, so that's omega squared, times the distance between the Earth and the sun. So that's the acceleration of the Earth around the sun. I haven't said what they are yet, but we can figure out what they are. Now, the acceleration of the swing is the rate that the swing goes squared times the length of the swing. So the two formulas look really similar, and we measured the rate that the swing goes. It swings once every 4 seconds about, and we measured the length of the swing, which was about 11 feet, or about 3 meters, what we're going to use. But before we put in the numbers, I'm going to rearrange the equation so we have just what we need to look at. So Newton's constant of gravity is on the top and the bottom, and so I can cancel it out. And what we're interested in is just the mass of the sun over the mass of the Earth. So I can move all the other quantities that are on the left over to the right. So now I have the rate that the Earth goes around the sun squared times the distance to the sun cubed. And on the bottom, we have the rate of the swing squared times the length of the swing times the radius of the Earth squared. So now we can just focus on what we need to do. So Newton's constant of gravity disappeared from there. So now we have to think about what these different numbers are, what these different values are. So the first thing is, well, what's the rate that the Earth goes around the sun? Well, it takes the Earth a year to go around the sun. And how we think about this omega squared, is the Earth goes around in a circle once a year. So a circle is 2 pi, and then we divide that by the length of a year, which is in seconds, about 30 million seconds. So that's 3 times 10 to the 7 seconds. That's squared. Now the distance between the Earth and the sun is 150 million kilometers. So I'm going to write that in centimeters because the length of our swing is also going to be in centimeters. So that's 1.5 times 10 to the 13 centimeters. And that gets multiplied by itself 3 times. So that's going to be a really big number. Now on the bottom, we have the rate that the swing went, which one cycle of the swing we also call 2 pi. And it takes about 4 seconds for each cycle. If you remember, it took 38 seconds to do 10 cycles. So that's squared. And then we have the length of the swing, which is about 300 centimeters. And the radius of the Earth squared, which is 6,000 kilometers, or 6 times 10 to the 8 centimeters. And that is squared again. So we have all these numbers, and we're going to have to keep ourselves organized. So the 2 pi on the top and the 2 pi on the bottom, they just cancel each other out. And I have 4 seconds way down on the bottom, and I have to square that. So I put 16 on top, and then I have this huge number, 150 million kilometers to the 3rd power. So if I go 1.5 times 1.5 times 1.5 3 times, it's about 3, close to 3. And then 10 to the 13 cubed is 10 to the 39. Now on the bottom, I have the year, which is a long time. 3 times 10 to the 7, I have to square that. That's about 10 to the 15. I have 300. And I have 6 times 10 to the 8 times itself. So that's 36 times 10 to the 16. So there's a lot of numbers here, a lot of big numbers, and we have to kind of arrange everything in a nice way. So I'm going to add up all the exponents on top. So I have 5 times 10 to the 40. And on the bottom, we have 10 to the 15 times 10 to the 2, which is 10 to the 17. And then we have 16 is 33. And then I have 3 times 36, which is about another factor of 100. So I have 10 to the 35. And if I divide that out, I've made a whole bunch of approximations here, but if I were to be a little bit more careful, I'd find that the answer works out to about 3 times 10 to the 5. With the approximations I make, I get 5 times 10 to the 5. So the ratio of the mass of the sun to the mass of the Earth is about 300,000. The sun is so much more massive than the Earth. And we can see that because even though the sun is so far away, it can still exert a large